Hey, everybody, and welcome back to another episode of Adventures in Machine Learning. I'm your host, Charles Max Wood. Quick shout out about the Dev Heroes Accelerator. If you're looking to be a dev influencer, go check it out, devchat.tv/hero. This week, we have a new panelist. We have Miguel Morales. And Miguel, you were on a few weeks ago as our guest, but do you want to just remind people who you are and why you're awesome?
Oh, wow. Well, my children say so that's pretty much it. That does it.
Super awesome. They got to me before the call, and our dad.
Yeah, no, it's good. So I'm a research engineer at Lockheed Martin, Missiles and Fire Control, particularly the Autonomous Systems Division. So I've been doing deep reinforcement learning research for a little while, and also I do a part-time. It's a instructional associate is the title at Georgia Tech, and what I do is basically it's like a glorified TA, so a TA with a lot of power and teaching and so on. But other than that, you're still responsible for grading or having others grade for you. But that's another fun thing that I do. And then, lastly, the book is one thing that I published recently. It's the Rocking Deep Reinforcement Learning, published by Manning Publications. So yeah, that's why my kids think that I am awesome.
Yeah. If you're doing missile guidance, that's almost rocket science, right?
Well, yes. No. Yes. No. It is not.
Yeah. So when we say, well, it's not rocket science, we're aimed at you. Anyway, yeah, we had a good time chatting the other day, and yeah, so we're gonna have more fun talking every week. We have our special guest here, Edward Raff. He's the chief scientist at Booz Allen Hamilton and the author of the JSAT. Did I say that right, or do I need to read the letters?
No,
machine learning
right.
Library. His research includes deep learning, malware detection, reproducibility in machine learning, fairness bias, and high performance computing. He's also a visiting professor. Boy, I feel so inadequate in all this professorship at the University of Maryland, Baltimore County, and teaches deep learning in the data science department. Dr. Raff. Ooh, I got this bio off of Manning, by the way. Dr. Raff, now I feel really inadequate, has over 40 peer-reviewed publications, 3 best paper awards, and has presented at numerous major conferences.
Thank you so much for the intro. And don't feel inadequate by anyone who has like a PhD. That just means that I've certifiably spent way too long on one problem than anyone ever should. That's all that means.
I know, right? It's like Edward's done all this cool stuff, and Miguel's done all this stuff. Check those podcasts. Did you work your tail off to get that senior developer gig just to realize that senior dev doesn't actually mean dream job? I've been there too. My first senior developer job was at a place where all of our triumphs were the bosses and all the failures were ours. The second one was a great place to continue to learn and grow, only for it to go under due to poor management. And now I get job offers from great places to work all the time. Not only that, but the last job interview I actually sat in was a discussion about how much my podcast had helped the people interviewing me. If you're looking for a way to get into your dream job, then join our Dev Heroes Accelerator. Not only will we help you get the kind of exposure that makes you attractive to your dream employer, but you'll be able to ask them for top dollar as well. Check it out at devheroesaccelerator.com. But yeah, let's go ahead and dive in because this stuff's really fascinating. That's why we have the show. It's fun, it's interesting, it's cool. But yeah, so we've talked a bit about PyTorch on this show, but do you want to give people kind of a high-level overview of what it is, and then we'll dive into how to do deep learning with it?
Sure. So PyTorch is somewhat similar to NumPy. So NumPy is sort of this very popular Python framework for manipulating tensors and matrices and just sort of doing math operations. And the wheel that makes deep learning sort of turn and move is really just sort of gradient descent. And PyTorch is an oversimplification is sort of NumPy with extra features to make it really easy to do gradient descent and really easy to use GPUs, which is sort of the two biggest things to like deep learning really taking off and being so successful that it's been today.
Gotcha. Now, pretend that I don't do this every day. What do you mean by gradient descent?
So the way I try to like explain it to people who don't have a strong math background is basically just sort of like an easy operation for trying to like minimize things. So you want to know like, okay, I've got some function and maybe this function is how much money I'm going to make this year. So I really care about this function. And there's inputs to the function, how much I work, how much I study, how many new skills I develop, whatever. I want to like, okay, what should I do to either, well, if I'm being weird, minimize this function or maximize it?
Right.
And gradient descent is basically just a math operation that tells you, here's the greediest thing you can do to try and sort of move this up or down, whichever way you want to move it. And
I gotcha.
yeah, that's sort of like the essence of most modern deep learning is we're just trying to set up a game where we've got some numeric score of how good is the network doing.
Mm-hmm.
And we're just trying to make that score better. And we're just following this dumb gradient descent greedy thing to something better.
Yeah, Miguel's nodding. Like, of course.
I can tell you another one. So you're in Utah, right? So you're familiar
Yes.
with mountains and things like that, right? So okay,
yeah,
imagine you're in the
I can see
mountain.
some out my window. Yeah.
Okay, great. I love them here too. So so imagine you're in a mountain, right? Down there's the river. You're thirsty, been lost for a few months. You really need a month, you'll be dead. But anyway, a couple of days, let's say.
This is getting
So you really want to
quickly.
get to the river, right? But there's fog, so you can't see the entire landscape. Gradient descent is going to help you go down the hill just a little bit at a time. So you start touching and say, okay, so here seems to be the best path going down. And then you touch, but you can't see the entire landscape. So that's the challenge, right? So if you could see the entire landscape, you can plan the route to reach the bottom of that mountain and get to the river, right? But you want to get to the river, you don't see the whole thing, but you start touching and say, well, okay, seems like this is the best path downhill. And then you get there and then go another step and another step and another step until you reach, right? So you have also gradient ascent, which, it would be the other way around. So let's say that what you want is to maximize to get to the top of the mountain. And then you would do the same thing, just touching around. I mean, it's simplification, but I think intuitively, if you have no background on deep learning, machine learning, and all that, I think that's a good intuitive way of looking at it.
So I guess my next question is, how do you know you've reached the maximum versus local maximum or minimum, local minimum?
Yeah, you don't.
You can't tell. You can only hope.
That's something that makes a lot of people queasy when they first sort of like about deep learning. It's like, well, how do you know it's like, so this gets you the best solution, right? It's like, no, it gets you a solution. Well, how do we get the best one? It's like, don't know.
Right. You should be happy enough you found the river and then that's it. Is it the best spot in the whole mountain? No, you don't know. And you will never know, which is the good thing. That's why we have jobs, right?
That's right. Well, then I'm just going to ignorantly declare myself king of the mountain whenever I want.
It's a good strategy.
I like it. All right. So deep learning. So I'm assuming the gradient descent is an approach to deep learning, correct?
I'd say so. I mean, it's definitely a big tool and component of deep learning. I do feel like the term deep learning has gotten a little more muddled in the past few years. It's sort of like everything counts as deep learning now.
Yes, that's fair.
Degree. Like if it isn't like something that already existed and you're continuing that line of research, so like if it already existed before, you can sort of keep that name. But if anything you're doing is new, you just sort of put it under the deep learning umbrella.
Okay.
And so I know a lot of people have sort of like different sort of vague sort of lines in the sand they draw around like, well, this box is deep learning. Outside of this box is not. I don't know. I'm kind of a big tent person. I just sort of like, let's get everyone here together and just like have fun and do cool things.
Sounds good to me. So you don't put a box around it?
I don't try to. And there's definitely things that I would consider not deep learning. Like if you're doing just sort of like some form of linear regression, or if you're using like a decision tree based model, that's pretty clearly not deep learning, I think. But then I go into the bigger tent of like, well, this is all just machine learning. And like, oh, I'm doing some like A star search. Like, okay, bigger tent, AI.
Gotcha. So when we're talking about this book, then inside deep learning and all the math and the setup and the algorithms and all the stuff that we're talking about here, how do you start approaching this, especially with PyTorch? Or does PyTorch irrelevant to it and it's just whatever tool you're using?
It's really whatever tool you're using. Like, I mean, you got to pick a tool to like give examples. I picked PyTorch because that's currently my favorite tool to use. But I tried to make the book very sort of not PyTorch specific. Like I don't really go into the details of PyTorch unless it's necessary to sort of accomplish something.
Okay.
I really
Let's just talk about the big ideas then.
Yeah, I mean, I think the biggest idea that, to me, what if I'm going to like start putting a box around deep learning after I talked about all my inclusiveness, what I really think about in terms of what deep learning is and what makes it useful is putting information we know about the world into the design of the model.
Okay.
So, like when we talk about like CNNs or convolutional neural networks, and a lot of people learn about those as just sort of like, oh, this is what started deep learning, and this is deep learning, and they know like, oh, you should use convolutional networks for images. They're the best for images. But part of what I try to focus on is like, why is it used for images? Like, there's a reason that it is, and it's because the operation called convolution maps very well to our intuition about like how images work. Convolutions are basically just like math speak for things near each other are related to each other.
Okay.
Which is how images work. Like if you look at this pixel and you've got my lovely blue shirt, and you look at any neighboring pixel, they're probably a similar shade of blue. And if you pick any pixel anywhere, that's almost always true. Everything around it is likely a similar sort of shade or color.
Mm-hmm.
And even when it's not, so like there's like the edge of like my shirt in the background, that edge sort of creates a consistent pattern. Like anywhere next to that edge is likely to also be an edge. And that's what convolutions sort of capture. And so part of what I try to do in my book is like, let's just talk about what a convolution is. Like what is this and why do we care? And how does that map to sort of embedding this information we know about the problem, images, into the solution, the sort of network's design. And I try to take that approach sort of with me through as much of the book as possible to sort of be like, okay, well, we're going to learn about autoencoders now. Like, what do autoencoders say about the problem? Like, why are we using an autoencoder? Like, why do we, if we use a denoising autoencoder, that's not denoising. If we use sort of a denoising autoencoder, or if we use like a contractive autoencoder where we're sort of creating a bottleneck, like why do we do those two different things? Like what are those trying to accomplish?
Right.
And really focusing on the intuition of how these sort of like building blocks work, and that you can sort of mush these building blocks together to create larger and more complex things. At least that's my goal. But I seem to like it so far, and hopefully readers do too.
I have a question. Can I? Right? Yeah.
Yeah, go for it.
Right. So would you say, Edward, that so convolutions are somewhat like, would you say it's like when you kind of blur the vision, right? Your vision, and try to kind of compress details into more, okay, I know that is you kind of thing. Or you think that actually convolutions would be more like sharpening and getting the details of things?
All right. Well, you can do both with a convolution, right? That's one of the things actually, like one of my pet peeves when sort of a lot of materials teach deep learning is we sort of like, okay, convolutional networks, like let's just sort of throw this convolution thing in here, but they don't separate out convolution from the network. It's sort of like one thing, but they're really two different things. So one of the things that I did in sort of the chapter on convolutional networks is like, let's just play with convolutions a little bit. Like, let's implement a convolutional filter to like blur things. I mean, look, it's blurry. Let's use a convolutional filter to find edges. Look, we found edges. And so we can sort of like see, like, you can actually get this very simple operation to do lots of different useful things. And I could look for all edges, or I could look for only horizontal edges or only vertical edges, or if I really wanted to, I could make angular edges. And it's like, okay, this is like this one thing is actually pretty powerful. And then we're stacking multiple layers of it. That's where it becomes sort of deep learning now. And you can just start to imagine of like, well, if one set of convolutions learned like this one learned to blur, and this one learned to sharpen, and this one learned like an edge. And then that becomes the input at the next level, which is now looking like, oh, what's the pattern of edges and the pattern of sort of like blurred inputs and the pattern of sharpened things. And I feel like that helps make it a little more intuitive of like why convolutional neural networks. and why we're stacking them up.
And so essentially what you're saying is you've got like a pattern for a mouth and a pattern for an eye and and then it also recognizes the shape of a face, maybe skin tones, right? And so it's like any of these skin tones, right? And so then it can start to recognize there's a person in this picture, right?
Oh yeah. Yep. Definitely.
And that's what the neural network does, because it layers all that on and then can make a judgment call and generally be correct about there's a face in the picture.
Yep. It's really, my real goal is really just sort of like help people feel more comfortable that they understand the intuition and it's not just like a regurgitation,
Mm-hmm.
So what other input data is, convolutions work for other types of data. Mm-hmm. Can you talk a little bit about the different uses there?
Sure. I mean, anything, this is sort of another thing that I tried, like, it's just convolutions are just the prior that things near each other are related to each other. And we can get into like the specifics of like the nature of that nearness relationship. But any domain where that's true, convolutions will probably do decently. So I have sort of a later chapter on like, you can use convolutions as an alternative to recurrent neural networks. And so if you have like a sequence classification problem, I want to classify this sentence as sort of positive or negative, is sort of the cliche example. You could use a recurrent neural network, that'd be fine. You could also use a convolutional neural network, and it might not have quite the same benefits as a recurrent neural network for that problem, but it still can learn sort of these words are next to each other, so they're related. And it can learn to do a pretty good job at classification. And it has some benefits in terms of being easier and faster to sort of implement and run. Actually, a lot of my own work has been on abusing convolutions for malware detection and sort of representing like, okay, you have some file, you want to determine if it's benign or malicious. And just saying, well, I'm going to process the raw bytes of this executable as one long sequence. And in our case, use a really, really wide convolution of like 500 for the width and use that to process the raw bytes because bytes near each other are related to each other and get it to learn, okay, is this benign or is this malicious?
So, now we're getting into training the system, right? Because it's got to know what malicious or benign generally look like, right? So you have to set this up and you've got to feed it a whole bunch of, this is good stuff and this is bad stuff kind of thing, right? So it can say, this is probably malicious, right? So where do you get that data from?
Someone spending a lot of time labeling things. I feel like that's
a grad student.
A grad student. That definitely happens. Well, the joke is like grad student descent for just getting grad students to solve a problem. I think that's something that's not in the book is like, where do you get your labeled data from? But that's something someone should write a good book on that. There's a lot of work that goes into just getting data and getting it labeled. Mm-hmm. I mean, you can go pretty far with unlabeled data and sort of unsupervised learning or semi-supervised learning, you just sort of get like a little bit of data labeled. But yeah, it's really just sort of like the unappreciated hard work of, well, let me collect examples of what I care about and document like, here's what happened, both like good outcomes and bad outcomes.
Right.
Then just sort of be meticulous about sort of getting as much and more as I can. And yeah, then training a model. And that really deals more with like my day job stuff of like, well, thinking about, is there some subpopulation that we're not getting good labeled data for?
Right.
Or something that we're not representing, or maybe our features can't represent something about some subpopulation, and important questions like that.
Well, and it's interesting too, because we've seen sort of ethical things raised where, certain algorithms don't recognize people with different skin tones or bone structures or things like that. But, to your malware example, for example, I mean, if I'm running your recognizer against my computer, I want it to find that malware, right? I don't want it to miss anything. And so there are implications for all of this, ethical or not, or business related or not, as far as, okay, what am I really looking at? It'd also be interesting now that you're talking about what is next to what, to look at like banking transactions, right? And what kinds of behaviors can I track down with that? I mean, when I travel, I'm typically, I usually stay at the same hotel chain because I get rewards points. And I usually make a stop at Walgreens or something or CVS because I can pick up snacks and I don't have to spend as much time or money on food and, figuring out where to eat. Right. And so then I just eat out once or twice. Right. And so you could probably pick up pretty quickly. Oh, Chuck's there for a conference because he did this pattern. And then, he only bought dinners because they served lunches at the conference or something. Right.
Mm-hmm. The malware one is I think it's particularly fun and interesting because there's a lot of unique problems there. Like there's banking malware that's targeted to banks. Like they send it, they're targeting just the big banks. They're really just trying to like get in and just like get a transfer of money to somewhere outside of U.S. jurisdiction, right?
Right.
And if you're a company or you're an individual, whatever, you will probably never see that malware because it's not meant for you. It's being targeted at specific entities. And so, okay, if you're a company, you want to build a good malware detector for your banking customers, like how do you get the examples that are targeted and sent only to them, especially if they're not yet your customer? Similar, like government agencies are going to get like attacks like just to them. The credit bureaus are going to get like attacks just to them because they have like this valuable information. So there's a lot of different sort of like niche subpopulations that you want to like handle correctly, but you don't have data for. And there might be niche populations you don't even know about. These are fun and challenging things to think through and important things.
Absolutely. So how do you pick the right pieces to put together, right? So that you can build this, I think the proper term is a model. So you can build a model for this.
Yeah, I think model's a perfectly good term for it. And it's really just sort of like thinking about like what are the properties in my data and in my problem. And I think for more junior person just getting started, you're just sort of like looking at the catalog of like, here's the kind of building blocks I know about. I have a convolutional building block, which has this sort of like things near each other are related to each other, sort of prior, if you will, something that we believe is true structurally about the problem. We have a recurrent neural network block, which is sort of a different spatial prior. It's sort of saying that these things occur in a sequence, and that sequence or that order is important. And the entire sort of sequence is important. We have attention building blocks, which are sort of a way of saying like, there's all these things, but the importance of any one component is relative to some context or the other components that are present. So like if I'm talking with you right now, you're very important. I think you're important. So I focus on you. I put my attention on you.
Why, thank you.
You're welcome. If the fire alarm goes off, no offense or anything, but I'm going to stop paying attention to you for a bit. I'm going to pay attention to the fire alarm.
Right.
Because the context has changed. And so your relative importance changes with like, am I going to be trapped in a fire? So learning about these different building blocks and sort of having them in your sort of like workbench to sort of think about like, well, does this building block make sense for what I'm working on or this problem is really the starting point for people to build their model. And then as you sort of get more comfortable, you can start to think about like, well, I'm not going to remember the name of the guy who said it. There's the adage like, all models are wrong, but some are useful.
I like it.
So it's like, okay, well, how is my model wrong? And is there a way I can make it a little less wrong?
Right.
So like machine translation is a really good one for like the like attention mechanisms really like came to form early on for machine translation. We're very good at it because you sort of had this approach of like, well, I'm trying to translate from one language to another. And so as I'm like producing the next word, I'm looking at the entirety of this entire sentence. But that's not how like people translate. You don't look at the entire sentence to predict like to figure out the one next word. You're sort of looking at like, well, I've translated this so far, and I want to do the next word. I'm sort of looking at like the specific location in the source language, the source sentence that I'm trying to translate. I don't need to think about the entire sentence. Like if I have I'm going to pick a dumb one because I'm really bad at all languages, including English.
Mm-hmm.
But if you're trying to translate like uno to one, like you need very limited context to do that. It's just sort of like a single word translation. But then if you want to translate, I don't know, like, so like,
watch out. I'm kidding. I can tell you.
so say
I speak
you're
Spanish. That's why I'm saying it. It's all good.
So you say you're translating like a gendered word from one language to a different language that like English, where it's sort of more like he or she and then the noun. So okay, now I need a little more context. So if I see that gendered word, now I need to have that context, like, okay, I need to sort of produce two words for this one word. Or if you're going the other way, I need to look at, not just doctor, but like some context where I get like a he or a she or a they. I don't know how you translate an ungendered doctor to Spanish, but I'm language dumb. But you need to sort of do a little bit of context just to find some pronoun that sort of tells you this missing piece of information to do a good translation.
Mm-hmm.
And so realizing, that's the way my model is wrong. Now can I come up with some sort of clever math to sort of better fit that?
No, that makes sense. And I don't know, Miguel, if that's how it is in Spanish, but in Italian, doctor is actually a really good example because you have dottore and dottoressa, and one is for men and the other's for women, right?
Yeah, it's the same. Doctor y doctora, and doctora.
Yeah. And so, you would use a different word depending on whether or not the person you're talking about is male or female.
Right.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
Yeah, no, and I think there are many differences to how you put the subject first or later. And, it's actually when I started learning English, it was a little difficult for me to actually switch those two and, try to make sense in English as opposed to in Spanish. And then there's a point you learn the two languages, you don't speak well either. You're like you lose a little bit of the Spanish and you don't get right there in the English. So you're like, struggling in both, but it's all good. By the way, I wanted to make a comment regarding the model thing, which is actually something that is very common too in reinforcement learning. So a lot of people actually want, in this case, reinforcement learning model or analogous to the model is going to be, or something happens very similar with simulations. If you're training an agent against a simulation, lots of people want that simulation to be a perfect model of the environment so that it can be basically you can simulate stuff and then put it into a real thing and magic happens. And it's pretty much impossible, right? Because like you said, all models are wrong, but some of them are useful. It's very interesting that lots of folks think that increasing the quality of your models is actually a better way to transfer agents from that simulation to the real world. And some research actually suggests that it's not that. It's actually randomizing all the different, models and having a bunch of different models that are very, very, very random or stochastic in this case, right? And then so that you can actually help your agent generalize across different models of the environment. And so that when you transfer that agent, the real world is just another model, right? As opposed to being a completely different thing. So I think, of course, we were talking about models as the machine learning model that learns to predict something in particular. But I think it kind of relates to what you were saying, don't you think?
I think a little bit of a tangent on a tangent. I think it's another fun thing so we tend to sort of humanize machine learning and AI a lot. Like, it's thinking or it's learning. I was like, it's really not, right? Like these are analogies because we like to think in analogies. It helps us understand things that we're not really like familiar with the inner workings of like the mechanical process that makes it work. But it sort of comes from and machine learning and deep learning is sort of like a weird one because we do this for everything. we humanize, we anthropomorphize, we do all of these things to help us understand new concepts or explain new things to other people. But machine learning trips over itself a little bit with it because we often actually use like cognitive science sort of results to actually help us like improve things. Like as we learn, like we know so little about like how the brain actually works, but there are things we do know. Like we learn about how we're able to do certain things, and we can often sort of take that like high level design idea and model it and get better results. Not always, but sometimes. So it's sort of like an interesting, something that makes this area sort of like uniquely interesting and fun in a way to sort of think about cognitive science things and like, well, like how do human brains like learn? Like, well, okay, like if I had a machine learning system that was as good as a human at learning, does that mean it's useless for the first like 18 to 21 years of its life just, like learning things? And we have to train this thing for 2 decades to like get it to be okay at like certain tasks? And like how much does sort of like innate knowledge passed from like genetic information matter? Like we've been evolving for hundreds of thousands of years, however long, millions of years. In order to train like a truly human intelligence level thing, does that mean we have to like do 20 years of like training and then like a genetic algorithm to swap the brains of like different things we've trained up and then like another 20 years? And so we just like have to simulate.
To be honest, I mean, if you check out population-based training, a paper published by DeepMind, it's one of the way of training reinforcement learning agents, right? You have the single models that learn, obviously, their particular task and whatnot, but then you have the population. So the genetic algorithm works across the different agents, and then it swaps agents and so on. So I think the idea behind it, the flavor of it is always going to be there. And by the way, what you were saying, actually, it's very interesting too. I actually attended a conference, RLDM, Reinforcement Learning and Decision Making Conference, not long ago, and it was very interesting because I went because of the reinforcement learning portion, but there were people that work in psychology, in animal thing, so they run a bunch of different experiments regarding the brain, right? And then to me, it was kind of interesting to see that they use reinforcement learning, so the research that comes from reinforcement learning to kind of test in their rats and things like that, and we in reinforcement learning use their work in animal behavior and human, of course, too, to kind of like create models and so on. So it's very interesting to see the relationship between the two. And yeah, we don't know everything about the brain, but that kind of synergy is actually pretty useful, pretty interesting.
I do think it's interesting that you also more or less made the point that where machine learning is an imperfect approximation of something that we don't completely understand.
Yep. We are miraculous, walking, talking, self-replicating automatons, and we have no idea how we do any of that, is my personal thesis. And we're just sort of figuring out that there's 2 wider perspectives on like people who say like, well, humans are the existence proof. It has to be possible because we do it. And I want to learn and figure out how we do it because that's probably the best way, because that's sort of like the thing that exists. And I'm more in the camp of, well, it's great that we exist. We know it's possible, but that doesn't mean it's the only way. It doesn't mean it's the best way. And what's best for like silicon may be very different than what's best for like wet, squishy brains. So let's just sort of like experiment.
Quantum, just seeing that quantum computers work so differently, it's that tells you that perhaps our brains really also work very differently than silicon, as you're saying. Yeah, and it's sometimes it's better just to be, how do you say this, like probably practical about it, and you need to solve a particular task as opposed to I'm gonna create a artificial general intelligence. That's really what I want, right? I don't really want another me in the house. I want somebody to wash my my clothing.
Is that you or your children speaking?
Right, exactly. No. Remember, they think I'm amazing, but when they grow, I know what's gonna happen. They're little right now, so right now they're in the stage of, oh, this is super. You are super. Yeah, wait until you're a teenager. But anyway,
Oh boy.
oh
Oh
boy,
no, let's not go there.
Duck knows.
Oy vey.
But I do want to kind of veer us back toward deep learning here for a minute because we're getting toward the end of our time. We've talked a bit about kind of composing the models. Can we go a little bit into just training and figuring out if we have a good model and fine tuning it before we wrap up?
Yeah, I mean, the biggest thing is to sort of, we have what we call our training set, we have what we call our testing set.
Mm-hmm.
And they should not be the same data, right? Because you don't, the way I like to explain it to people is, again, these they're not learning like we do. They don't understand, the algorithm does not understand your intention. It only understands the specific numeric sort of game that you set up to sort of maximize. And that means if there's any way to sort of cheat at the game, it'll do it. So for making a good training and testing set, we want to make sure that there's as little ways to cheat as possible. So if you use the same data to train the model and then see, like, do I get the right predictions? You can cheat by just memorizing the answers.
Right.
I saw this data point and this was the answer. I don't understand why, but I'm just going to learn to regurgitate that this data point gets this answer, which will pass the test, but not be actually useful.
Right.
And that's basically how we figure out, like, are our models good or not, is we make that test set, we train the model, we then run it on the test set and see how many of the answers are right or wrong. And we say, how good that is depends very much on, like, context and problem.
Mm-hmm.
If you're trying to predict if something's like a hot dog or not, that's a pretty easy problem. You should be able to get, like, really high accuracy, right?
Mm-hmm.
If you're trying to predict the weather for like a week out, that's hard, but not super impossible. So you go, okay, if I'm off by like 7 degrees in either way, that's actually okay for 7 days out. That's pretty good, actually. If I'm trying to predict if my joke is going to land and people are going to like it, like, that's 50. That's really hard. I'm
Right.
not good at them.
If you have a classifier, I need that one. So
I know, right?
Exactly.
I've made no progress.
Yeah. Speaking of teenagers, yeah, my audience of 2, I get eye rolls all the time.
All the time, yeah.
I consider groans an acceptable form of compliment.
I drive them to school every morning and drive them crazy with, yeah. Anyway.
No, but on the training and testing set, though, I think it's good to hammer home, like, the cheating aspect and, like, thinking about ways that you could cheat if you don't sort of split the data well. So, like, if we have, like, oh, I'm trying to predict the weather sort of in several days out or something. So, okay, I want to make sure that I don't have the weather for Wednesday in the training set if I'm going to have Wednesday's weather in the testing set.
Right.
But it's more nuanced than that, because if I have Monday, Tuesday, Thursday, Friday in the training set, Wednesday's in the middle, well, I'm guessing Wednesday looks something like the average between Tuesday and Thursday. And that's probably going to be something pretty accurate without actually understanding how to predict what the weather is. So in that context, we actually really need to sort of have, like, a split in time to sort of minimize cheating, because you have sort of time traveling going on. If time is important to your problem, you have data from, like, X and Y, and your training data and your testing data has something in that range. Your model has the opportunity to have, like, seen the future to try and predict the past. That's cheating.
Right.
And just, like, coming up with different ways and sort of having this Machiavellian mindset of, like, well, how could I, if $1 million was on the line for me to, like, maximize this score, like, what would I do? Just trying to maximize the score. And for any ideas you come up with, trying to make sure that you sort of mitigate them in how you separate your training and your testing data is, I think, probably the biggest error I see more junior people make. They sort of just do random training and testing set splits and, oh, that's good. But, well, maybe not. Another one, if you're doing like anything health related, if you have multiple data points from the same person, and if you do it randomly, you get some data points from Edward in training and some data points from Edward in testing. That's cheating. You've already seen Edward before. We want to know how well the model does on some new person you've never seen before.
Right. Makes sense. Makes a lot of sense. All right. So how do you fine tune it then? Do you just give it better data
That's one
when
option.
you train it?
That's
Okay.
the unlimited money and budget option. Yeah, getting more data, getting better data, trying different sort of models and hypotheses. So you can sort of use something when people get really good and they sort of really understand, like, how does this model see the world? Try lots of different models and see how different ones succeed and fail, can tell you or give you feedback about what things might be true about your data, is a really useful thing. And then that can help you, okay, I've done this, I tried. So you might say, like, well, I tried a convolutional network, I tried a recurrent one, I tried this attention one, and I understand these are how these different models relate to each other and what they assume about the world. Here's how they did. I might use that to inspire myself a new architecture I might design. That's more of a bit more sophisticated approach to trying to get better. The other thing you can do is just sort of like keep tweaking parameters. So, like, how many layers do I have? How many neurons per layer? Which activation function? There's lots of knobs you can tune and just sort of keep trying and adjust those little knobs and see if it does better, which is still good to do. Yeah, those are really the main couple ways that you'd go about it.
I'm curious, Miguel. I mean, we talked about reinforcement learning. And so if we put these two ideas together, how do they relate? I guess, Edward, you can chime in too.
Yeah. So I think so. Edward was talking first about the model kind of cheating, and I think that in reinforcement learning, that's actually a very big deal, a big issue. Then there is this, I'm going to call it a field, explainable AI, which is related to looking at trying to explain why models, in the case of reinforcement learning, why agents make decisions. And they do this through trying to look at the if it's a convolution, for instance, you can inspect the network and so on. But I think that's just a single example. Of course, there are many other techniques, and I think the field is going to become more and more important and relevant as we continue, right? But I think in reinforcement learning is a pretty big deal because humans not only want to have optimal behavior, but they also, for some reason, want to understand it, right? Why did AlphaGo make that move in there, right? So, sometimes, it's kind of hard, but, if I'm in an airplane, I don't care about the pilots, like somebody vetted the pilot. I'm not trying to understand every single move. Otherwise, you go crazy, right? But for some reason with AI, it is not such. And I think that's maybe a good thing in the short term. I think long term, we're just not going to be able to keep up. And in reinforcement learning, you see lots of those examples, right? So in very interesting, your AI is basically learned to break your simulation very easily, and then for instance, I think I'll give you a very short example. If you have an aircraft, right, that is simulated, that you have the behavior is actually inside of the simulation against an AI, the AI is going to quickly find holes in your, let's say, I guess it's called like behavior tree, right? So if this happens, do this, and so on. And that's when things such as multi-agent reinforcement learning come into place. You actually have AlphaGo was a very good example of that. They trained that using self-play, which is the AI against itself, or close versions of itself, not necessarily the exact same version at any given time. And that's actually much better because the simulation does not try to. So the holes in the sim, or the ways in which the agent can cheat are minimized in order to win, are minimized in that case. So no, I think that the point is a very big point, and it has lots more to it, definitely.
Yeah, the explainability one in particular is I think really important and interesting, in part because I think some of the maybe slightly misplaced focus currently is on making it explainable, I think, to laymen rather than making it explainable to an expert. Because one of the things, it's sort of this Russian nesting doll, like, well, if you make it explainable, how do you know that the explanation is correct? Like if the model could just put out like a human English language sentence saying like, this is why I made this decision, how do you know that's actually why it made that decision?
Right.
Then you need
a Pandora's box, right? I mean,
yeah, then you need an explanation for the explanation.
Yeah.
So it becomes very challenging to sort of make something like that, which is why I lean more to encourage sort of like explainable to an expert, so that there's like, you have a bit more of that, you have like diagnostics, you could figure out what went wrong, which I think more closely aligns with how we handle a lot of like important safety situations, like an airplane. Like a big thing is like, well, if something goes wrong, we need to be able to figure out why, so that we can fix that problem for the future. Which is not to say that like, I'm not poo-pooing any research on like, can I get an algorithm to literally just like spit out human English on like why it made a decision? Like that's still cool research. I just think a little more like overemphasize that like, oh, if we don't have like this, we can't use it. It's like, well, maybe not. We should sort of balance like what could go wrong in the worst versus like degrees of explainability to whom, and sort of if there are rail guards that are in place to sort of prevent like, oh, if the algorithm makes a dumb decision, like it's just deciding like what I eat for lunch. And it gives me like a salad. Like salads are gross to me. Salads, but I'm not going to die.
Maybe.
Maybe.
I do have to say though that, people put the explainability, onto the machine learning, and in particular, when it's executing, some kind of complex thing like a Go game, is the example that Miguel brought up. And what's funny is you're looking at it and you're going, okay, well, what's the overall strategy? And the reality is that the machine has been trained over and over and over again and has run scenarios over and over and over again, has the proper weighting in its neurons to make the decision. And so the reason it made that decision is because when it ran through everything that it had, that was the most likely, given all the possible outcomes that can come next, that's the most likely one to bring it success. It's not actually trying to corner this set of pieces. It's not thinking that way at all. What is thinking, if it's thinking, is okay, this is what I've got, these are all my inputs, and so therefore this, if I put a piece here, this is the most likely avenue to success. And so we attribute all of the other context that we put on a Go game to that move, where in reality, and you may be able to extract a cohesive strategy from the way that the machine plays Go. But the reality is it's just playing because that's the most likely, given everything that it's been trained on, to give it success.
Oh, definitely. I think it speaks a little to what we were talking about before about sort of like humanize things. And like, well, this is the way that we think about things, but like doesn't mean that's the way that the model is coming to a decision. And there's context where like it's really important to know how the decision was made. It's like, okay, well, maybe we just use something other than deep learning. Maybe we use a decision tree because that's very human interpretable. And we can literally look at the decision tree and be like, well, that makes sense. Or, well, that's a stupid decision there. Like, let's cut that part off. That doesn't make any sense.
Yeah. I mean, to that point, I can imagine, for example, that we apply this, say, to, given our current situation, giving out vaccines, right? Each state's making its own decision on how it does it and who gets it and, all this stuff, right? So let's say that we apply a machine learning algorithm to figuring that out, right? And it figures out that, compared to our current methods, it could actually give it out and, save 20% more people, right? In the long run. So that then we start looking at it and, then we really do want to, understand what the difference is, right? Because it's a probability isn't a good enough answer. Why? Why does that matter? Why does it make a difference? What are we trying to do? Because at the end of the day, we have an outcome that matters, right? Because it's real lives. But the other thing is can we extract this to other public health things that we do And so there's real meaning to it, right?
Mm-hmm.
And I could see that kind of going in a direction that's interesting as well.
Yeah, that would definitely be an important situation where you want to understand how it came to that decision, because you want to know that it's actually going to work, because you only sort of you get one shot.
That's true.
You can't just go back in time and be like, oh, let me do that month over again. That vaccine rollout month didn't go as I like, so let's mulligan that. That month is gone. So yeah, that's definitely a situation where you really want to understand what you're doing and why.
Yep, absolutely. All right, we're kind of at the end of our time. Before we wrap up, though, Edward, if people want to contact you or find you online or see what you're working on these days, I'm assuming GitHub, Twitter, those are usually the places people are at, but are there other places as well? And how do they find you on those platforms?
Yeah, edwardraff.com gets you to my website. There's a beautiful picture of me. And yeah, Twitter, at Edward Raff ML. My emails are on my website. Most of my work's on my website. You can sort of find the things that I'm working on there.
Yeah. So you said a beautiful picture of you. I'm assuming you wrote a machine learning algorithm that determines beauty, ran it against your photo, and it told you, right, that you're gorgeous. So
no, you just told me earlier that I looked nice. So I just assumed that you would like my picture.
He said a beautiful picture of me, not a picture of a beautiful me, which is
okay.
Right? He had a really nice background, flowers in the back. That's all.
My language parsing needs some work. All right. Well, let's
get good at racism.
Yeah, absolutely. Let's do some picks. Hey, folks, I don't know if you've noticed, but I've been working a lot on figuring out how to help people become the most valuable developers on their teams or becoming the top 5% of developers in the field. If you're looking to level up, figure out how to contribute more, get the career you want, get the career that you want that will support the lifestyle you want, then you should check out the Most Valuable Dev Summit. I've invited some of my friends across the community, people that you've heard of, people that have worked on systems that you use on a daily basis, people who have invented new ways of doing things over the years in programming, and I've asked them one question, and that question is, how do you become a top 5% developer? How do you become 1 in 20 of the best developers out there? And so we're going to go ahead and have that conversation with them in interviews on the Most Valuable Dev Summit. And you can find that at summit.mostvaluable.dev. Miguel, do you want to do some shout outs about some stuff you like?
Sure, yeah. Let's see. I actually, this time I looked it up. Let's say I was prepared. No, but I think that, so for folks who want to learn deep learning and don't have too much of a math background, I think sometimes it's useful to get hands-on experience. So shout out to the full stack deep learning course available for free. These guys are teaching you CNN, computer vision, RNNs, transformers. I mean, pretty interesting stuff. ML projects, infrastructure, tooling, all that, and they do have labs. So check it out. I think it's a little bit advanced. I mean, for folks who are brand new to the field, but I still recommend it. I think that even if you don't know, you want to just but you have time, that would be a really good resource. So I recommend that one. Yeah.
Awesome. And I like it too. I mean, even for new people, I always learned best when I got way out of my depth and then started asking questions. So I like the recommendation. I'm going to throw out some picks. One of them, I've just started getting into Docker. We use it at work, but somebody else set it up, right? I have this big fat Docker Compose file on the Rails app that we're working on. And, and so I just Docker Compose up, Docker Compose down, and then help, it's not working. So I've been diving into it and really figuring out how it all goes together. Hit some snags, but that's always part of the learning process. And I'm actually really liking it. The thing that I really like about it is that it allows me to isolate the environments I'm working in. So if I need a different version of a language or a framework or a tool or whatever, or a database, I can stick it in Docker and then just Docker Compose it. And it works really well. I know this isn't our DevOps show. We have one of those. You can go check it out. I'm on that one too. But yeah, it's a super handy tool. So I'm going to shout out about that. And then my wife and I have been watching, we just finished the last season of Star Trek Discovery. And when the season started, I wasn't sure if I was going to like it because it kind of went a little bit different. But it it kind of explored some areas of some of the characters that you sometimes don't get in some shows, because they could put them in some really unique situations and then force you to really think about where they were at and what's going on. So it's funny. As much as I love science fiction, I watch shows for the characters. I will just put it out there. I watch shows for good characters, and they've got some really interesting personalities that come together in different ways. And the character growth and the journey, I just really enjoy it. So I'm going to shout out about that too. I think it's only on CBS All Access. So if you're looking for that, you might have to pay for a membership. But those are my picks. Edward, what are your picks?
I'm going to throw out Java as a language and tool for machine learning and data science. I know Python is all the hotness and rage.
I think you hurt some people's feelings, but keep going.
I think more people would be amazed that, like, I'd say Java is actually my favorite language. I get more odd looks for that one than anything else. But static typing and sort of all the tools, especially the standard library in Java, are really nice. It's part of why I have my machine learning library written in Java. So I really enjoy that, and I encourage people to sort of branch out more from Python to other static sort of fast languages. Sort of learn Rust, learn C++. I think would really help grow a lot of people's skill sets. And then I'm going to go sideways for the other thing. Well, my book as well. Go read my book. But I mean, I did put a lot of work into the book. I do hope it is helpful to people. But outside of like technical things, I'm going to throw out the Make-A-Wish Foundation. It's a great charity, and people aren't familiar. It basically help children who have terminal or really life-threatening diseases, sort of like what do they want, and like try to like help them make that happen, whether it be like meeting a specific person. I've helped do wishes before where it's just like they wanted a computer. Their family couldn't afford a computer. They want to be able to play video games. And there's a lot that you can do and help with, where it might not seem like it at first, but it can really like change someone's life and make their life much easier when they're in a really, really tough situation. So I'm going to throw that out there as my favorite charity, and people should take a look at it.
Awesome. All right. Well, I think that's pretty much all we've got. I love the pick. People should definitely go check that out as well. Is there an easy way to get involved with that particular charity with Make-A-Wish?
You can find out more through the main website, and they also have local chapters for different states and larger cities. And you can donate time to help make wishes happen, or you can donate money. I've done both.
Okay.
Especially if you've never done I assume most people haven't done a wish before. It'd be weird if most people had been involved with a specific charity. But and I honestly, I don't do as much anymore because it is very emotional, but it's also very rewarding. And it's something I'm very glad that I have done, supported. And yeah, you can find out more on the website. Or if you're having trouble finding it, email me and I'll help you find what you need.
Awesome. Sounds good. All right. Well, let's go ahead and wrap this up. Thanks for coming, Edward. This was awesome.
Yeah, thank you so much for having me. I really enjoyed it. It's been a blast.
All right. Well, we'll wrap it up here. Until next time, folks, max out. Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.